Hi, this is Brad Strebig, and today we're going to talk about the ideal gas law. Last time we talked about how we used various chemical properties to determine the concentration of different compounds that may be dissolved in water. Today, we're going to look at things in the gas phase, how different compounds are in essence dissolved in air in the gas phase, and how we determine those concentrations in unit conversions. The basis of this unit conversion process is going to be the ideal gas law. So for our purposes, we're going to assume that most gases act under ideal conditions. In most places on the Earth and most environments, this assumption is a relatively good one. As our pressures are close to atmospheric pressure, our volumes are what they are, number of moles are a given property, the ideal gas law constant is a constant, and the temperature is usually close to environmental temperatures, not too extremely cold or not too extremely hot. Under those conditions, the ideal gas law may not apply, such as volcanic vents or certain areas of Antarctica. But for most environments, we can use these purposes to determine the concentrations of compounds in the atmosphere. Let's recall the volume fractions of each of the major gases in the atmosphere as they were listed in Table 2.1. For nitrogen, if the total pressure of the atmosphere is, under standard conditions, has a pressure unit value of 1 atmosphere, the percent or fraction value of nitrogen in the atmosphere is 0.7808, or about 78%. So the fraction of the atmosphere, the pressure that is exerted by the molecules of nitrogen in the atmosphere, is 0.7808 atmospheres. We can convert this to pounds per square inch and find out that the nitrogen in the atmosphere presses down pretty much everywhere on Earth near sea level at an average of 11.47 pounds per square inch. So that's the weight of the air upon each and every one of us, or at least the nitrogen component of the air. Similarly, for oxygen, that makes up about 21% of the air, so 0.2095 atmospheres, or 3.08 pounds per square inch that oxygen is pressing upon us. Are you beginning to feel the weight of all this yet? For argon, the third most common compound, at about 1%, that has a pressure that is exerted about 0.14 psi. If we sum all these partial pressures in the atmospheric values, we get 0.9996 atmospheres. Thus, 99.96% of the dry atmosphere, that is, the atmosphere if it doesn't contain water, is composed of just these three gases. So when we talk about air, we're talking mainly about nitrogen, oxygen, and argon. Other things that we're concerned with in air, such as carbon dioxide, other greenhouse gases, potentially acidic gases, and other compounds that might be health concern, are again maybe of very, very low concentrations, less than 0.4% in general. So we need to be able to have units that express these small concentrations of pollutants in the atmosphere. For the gas phase, we're going to rely on a volume fraction rather than a weight fraction. Let me repeat that one more time because this is very important. For water, there is a relationship between volume and weight that was very easily because that's what the metric system is based on. 1 gram of water per cubic centimeter. Water is very dense compared to air, so air obviously has a much different density. So we do not typically use a weight fraction, but we rely on the volume fraction of compounds in air, because volume is a term that's readily accessible from the ideal gas law. So we define a volumetric part per million as 1 part volume of a compound per 1 million parts volume of air. So again, ppm by volume is a mole fraction or volume fraction that's commonly used to describe the concentration of pollutants in the gas phase. But the conversions between weight and volume and parts per million is much different for the gas phase because of the difference of density between air and water than for the water phase. So let's look at some examples. First, let's look at how we define a volume fraction. Here we have a simple mixture of 0.001 moles of sulfur dioxide, a common pollutant from burning coal, and 0.999 moles of air, a very common percentage value for the nitrogen and oxygen in the atmosphere. So how would we express this SO2 concentration in parts per million volume? Well, according to the ideal gas law, the moles of the compound is proportional to the total moles of gas. We multiply that times 10 to the 6, and in this case we have 0.001 moles of sulfur over the total number of moles, which is 0.001 moles of sulfur plus the 0.999 moles of air. We multiply that by 10 to the 6 to give us the value in parts per million, and we find that there are 1,000 parts per million by volume of SO2 in this example. Another skill that you'll need to be proficient at, proficient meaning able to do very quickly, easily, and consistently, is conversion of this mole fraction to a mass density in air, because many times we're interested in the pounds, tons, or grams of a compound that's emitted into the environment. And we'll discuss this in much more detail in Chapter 5. The concentration is the mass per given volume. When we rearrange the ideal gas law concentration to have the mass per volume, that's going to equal the pressure over the temperature times the molecular weight of the pollutant in the air over the ideal gas law constant. That's going to give us the volume fraction times the pressure of the given compound over the temperature. If we substitute these values, the total pressure, P sub T, is 1 atmosphere, and Y sub I is the volume fraction of our compound. If we have a temperature of 289 degrees Kelvin, our standard temperature, the ideal gas law of 0.8206 liter atmospheres per mole degree Kelvin, at standard temperature and pressure, and converting to units of milligrams per meter cubed, the derivation for which is in the textbook, we see that the concentration of something expressed in milligrams per meter cubed of air is equal to that concentration expressed as a volume fraction or mole fraction in terms of parts per million multiplied by the molecular weight of that pollutant divided by the values of the temperature and ideal gas law constant and standard pressure all multiplied together, which gives us a value of 24.5 in the denominator. For non-standard conditions where we have a non-standard pressure or temperature, the concentration in units of micrograms per meter cubed is equal to the concentration in parts per million by volume times the molecular weight of the compound multiplied by 1,000 times the pressure of the system divided by the ideal gas law and the temperature. So let's remember that the density of water is different than the density of air. So we get a much different relationship between the mass conversion values, and in your textbook you'll find these conversion equations as expressed as equations 219 and 220 in the textbook. So let's look at an example of a conversion of gas concentrations between, in this case we're going to use parts per billion by volume, and micrograms per meter cubed. Again, very small levels. We'll look at measurements that the EPA conducted for what they call criteria air pollutants, or important air pollutants that the US EPA measures, near Washington, D.C. in Fairfax County. These values were recorded in 2008. Let's do one example, and you can do others on your own. We'll look again at the sulfur dioxide, the SO2, which had a value of 16 parts per billion measured in the air. We would like to convert that to a mass fraction value of micrograms per meter cubed. In order to do this, we have to note that 1 part per billion is 1 part per million over 1,000. So 1 times 10 to the 9th is a part per billion. Also, a microliter is equal to a milligram per liter divided by 1,000. So that we can use the same expression since both values are divided by a factor of 1,000 from the equation in the book, 219. Substituting in then the concentration in micrograms per meter cubed is going to equal our 16 parts per billion by volume times 64 grams per mole, the molecular weight of the sulfur dioxide, divided by 24.5, will give us a conversion value of 42 micrograms per cubic meter of air. So they're only going to be in a cubic meter of air. You can visualize that. So if you're looking at a computer screen in front of you, you can stack approximately a couple of those on top of each other in a box about that high, that wide, that long. In there would only be about 42 micrograms of sulfur dioxide. And we're measuring things at these levels in the environment, which can impact the environment, as we'll discuss much more in Chapter 5, the chapter on air quality. So I'll leave you with an example to work through. If we have a marble that weighs 1 milligram, and it has a molecular weight of 20, and green marbles that have a molecular weight of 40, what's the concentration of marbles in a half-liter jar filled with water in milligrams per liter and parts per million? You can vary the numbers and kind of play with this idea a little bit. But as you think about this, think about how the difference is between if those marbles were in water or if those marbles were in air. How would the weight of that container be different? The weight of the container with the marbles in air would be much different, much lighter, right? So the way that we calculate the mass values is going to be much different as well. In water, common units are milligrams per liter and parts per million by mass. And in air, common units are milligrams per meter cubed and parts per million by volume. Practice these conversions, either using the marble example, make up your own examples, follow the examples in the book, and practice the homework problems. Only by practicing these procedures can an engineer become proficient, quick, reliable, and easy to do, easy to remember. The engineer must be able to convert between these units of mass, volume, and concentration in order to give a quantitative definition to sustainability and environmental impacts that we'll be talking about throughout the following chapters of this textbook. It's very important to practice and practice and practice these conversions so you understand them and can use them as we move forward in the text and in the course. Thank you. In the next section, we'll be talking about the chemistry of natural systems and using these unit conversions to describe the concentrations of various things in water and in air.